Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to talk about the Gram-Schmidt process. And before I get on to all this procedure here, what I'm going to do is I'm going to recap on what you have learned before. So previously, you might have an orthogonal basis, and you can transform that orthogonal basis to be orthonormal basis. Okay, so the transformation here, where for example, if you have this vector 1, vector 2, vector k, which is the orthogonal basis, you can then transform that by having orthonormal basis when you consider the magnitude of each vector and divide this vector with its magnitude. So v1 will be divided with the magnitude of it. Similarly, v2 will be divided with the magnitude of it, and it goes on for the last vector here, will be divided with its magnitude. So by doing that, you get a new set, which is an orthonormal basis. Now, we might want to find the orthonormal basis when given any regular basis. So for example, now we might have any basis. So how can we transform any basis to orthonormal basis? Okay, and to do that, we require the Gram-Schmidt process because it makes the thing a lot easier. Okay, so in this process here, what happened is we can have any basis. So what happened is we have any basis, and then this basis here, using the Gram-Schmidt process, you can turn this basis into orthogonal basis. So this is using Gram-Schmidt process. Now from orthogonal basis, so now from orthogonal basis, you want to get orthonormal basis, then the transformation here will follow the same idea that you have seen in this part. Okay, so basically the Gram-Schmidt process will help you to turn any basis into orthogonal basis. And once you are at this stage, you can get the orthonormal basis by applying this transformation procedure here. And in this Gram-Schmidt process, you will see the idea of orthogonal projection being applied, and I will explain about that as we go on, and without further ado, I think we should look at the process, or how can we do this. So this process here looks daunting, and it's a bit difficult to try and understand what's going on at all this particular stage. So I'm going to recreate and explain what is this process all about. So if you are ready, we can just you should get like pen and paper and try to do this along with me. Okay, so we are going to try and do it on ourselves. We do it ourselves to try and get this part, try and understand how this comes about. Okay, right. Now, so given that, so in this case we have a set of this vector x1, x2, and xk. So this can be any basis, and our interest is to transform this so that it becomes orthogonal basis. And orthogonal basis here is, according to this formula here, is denoted by V1, V2, VK. So this is just notation or alphabets. You know, you can choose any alphabets if you want, if you don't like X or V, so it doesn't matter, okay? Now, so to transform X from X to V, what we can do is, for the first step is quite easy. You want to know what is the value of this first vector. So first vector here is just equal to vector X, so X1 from this basis. So V1 is equal to X1. So that is the value of this vector. Problem solved for V1. Now what about V2? For V2, it's going to be X2 minus, now notice we already have vector 1, so here we have already got the value of this. Therefore, we are going to consider the projection of, so this is the old one, so we're going to project this onto a new one. So we're going to project X2. So here is, we're going to project X2 into this, and we don't know what that is. So projection of X2 with respect to what we already know. So here is V1. We already get this result. So we're going to project that with this vector 1. Okay. So similarly, for V3, if you want to look at V3, that will be X3. So you follow this notation. So you want to know what is V3. V3 is here. So what you have is X3. The vector is X3. So you will have to minus the projection of X3. And you already know V1. So we're going to do that onto V1. Minus, we also know what is V2. So we're going to do that projection of X3 with onto V2, because V1 and V2 are already known. So that's the idea. Now let us try one more time. So what is V4? Let's say we have V4. V4 means we are going to consider X4 here. So X4 is from this any basis. So this is X4 minus, so we're going to project X4 into what we already know. So into this vector 1. So again, we need to find the projection of X4 into what we already know here, which is vector V2. And we're going to do this for V3 as well. So projection of X4 into V3. So the pattern is like that. And if you do it, because you have xk, so of course you're going to have vk. So what is the new orthogonal basis based on this? So that will be vector k. And here I'm sure you can guess what is this going to be here. So it's going to be xk. So this is the old one. You can think of it as something already given. So this is something new that we don't know what it is. So xk. So we're going to project what we have here, which is what is given. So we're going to find the result of projection of xk to what we already know. So we're going to start from v1 minus projection of xk with respect to or onto v2, projection of xk onto this v3, and then projection of xk into, of course, v4, and we've got to continue this until the last item. So that will be projection of xk, and you can see since you can see this pattern here, well, for example, V2, we stop at until V1. So here we got 3, so here until projection is up to V2, of course. We have 4 here, so the projection will be of x4 until V3, because V3 is the last information that we have. So therefore, if you have here k, so this will be k minus 1. Okay. So that is the pattern, and I hope you can see this pattern clearly. Now, based on this pattern, you can see that for this part here, you need to be able to be comfortable with the formula of orthogonal projection. So here, this is equal to, okay, I'm just going to write down here. So this is equal to, we're going to project x2 onto v1. Therefore, we are going to have v1. We're going to have v1 and v1 here, and v1 outside, and here will be x2. So x2 appears here, and here is v1, 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 v1. So if you look at this part here, this is the projection of x3 onto v1. So clearly we are going to have v1 dot v1. Here is also v1, and then this will be x3, what we're going to project. Okay, so you can see, so x2, here is x2. If you're going to project x3, so here there will be x3, and this is onto the particular vectors. We're just going to replace all this with that particular vectors, and I'm sure you can sort of understand what's going on for this one. So want to try and do it along. So here, that means projection of x3 onto v2, which means we have v2 dot v2. Outside here is going to be v2 multiplied with v2, and here it will be x3. So I hope you can see this idea that, you know, when you consider all this, you will have the process as given here. Okay. Now based on the process, all this value here, so v1, v2, v3, vk, this is an orthogonal basis. Once you have orthogonal basis, you can move on and transform that to orthonormal basis if you want, or if the question asks you to do. Okay, so let's look at the example. Here we have W, this is the vector space, span x1, x2. So therefore, x1 and x2 here is any basis, is a basis of W, okay? So based on this, I'm just going to call this as x1, x2, and I can write this in this representation, and x here is just any basis. Okay, it doesn't give you any indication whether it's orthogonal or not, so we can consider that to be, you know, whatever basis, any basis, it is not orthogonal. And of course it is not orthogonal because the next line here is asking you to apply the Gram-Schmidt process to construct an orthogonal basis. So clearly this one here is not orthogonal, okay? Right, now we're going to do that. We're going to follow the procedure which I have outlined previously. So here is x1 and here is x2. Since we have two items here, of course the new one also we will have v1, and the starting point is v1 must be equal to x1. Okay, so v1 is x1, the new vector here, v1, and this is equal to, just plug in the values, 1, 1, 0. Okay, Next is V2. So again, when you see this is what we want the new vector V2. So it will be the given vector x2 here. So it will be x2. And we should minus the projection of x2 because x is given. So we're going to project x2 onto something that we already know. So we already know what is v1. So we're going to find the value of projection of x2 onto v1. So that's where we stop because we only know v1. And this is equal to x2 minus, well, if you want to project x2 onto v1, the formula is going to be v1 dot v1. Outside here is v1, and on top here it will be x2. So that's a formula. Okay, so now what is all these things? So we need to find what is this value. So for example, for the numerator, I have to find what is v1, the dot product of v1 and x2, and this is equal to 1 1 0. So this is v1. x2 is this term, so this is negative 2 0 1. Based on this, I will have negative 2 0 and 0. So this is negative 2. Next, I need to find the value here, which is the dot product of v1 and v1. So here will be, again, this is v1, so 1 1 0 dot 1 1 0, and it becomes 1 plus 1, which is equals to 2. We're just going to substitute the results here into this part. Well, x2 is this one, negative 2 0 1, minus v1 x2 is negative 2 over v1 dot v1 is 2, and factor 1 here, v1 is 1 1 0. Then what we can do is we can simplify the process here. So we have negative 2 0 1, this becomes plus negative negative plus 2 over 2 is 1, so plus this factor here, and finally the answer is negative 2 plus 1 is negative 1. This is 1, this is 1. So this is the answer, and this is the orthogonal basis for W. Okay, sorry, this is not the answer. Yeah, I'm sorry. So this is just the answer for V2. Therefore, orthogonal basis for W, we need to consider the combination of all these two vectors. Okay, hang on, let me just erase this. So therefore, orthogonal basis for W is just a set of vector 1, v1 and v2, and that can be written as 1 is this, so 1 1 0, and here is negative 1 1 and 1. So this is orthogonal basis for W. Okay, right, now let's move on to the next example here. Okay, so we have 2 more examples to do. So for this example, B here is the basis for this vector space, and the notation here is V. So here is V1, V2 and V3. You are asked to find the orthonormal basis. That means you have to turn this basis into orthogonal first using the Gram-Schmidt process, and then you're going to turn that orthogonal basis into orthonormal basis. Okay, right, therefore what we're going to do is we're going to apply the Gram-Schmidt process straight away and find the orthogonal basis. Okay, this is the first part maybe. So to find the orthogonal basis. Okay, since this is using vector v, so I'm just going to use vector u for the orthogonal basis. Okay, so I'm going to just use u, or if you don't want to, confuse vu and stuff like that, we can use other name for that new orthogonal basis, vectors of orthogonal basis. So I'm just going to call this vector maybe w. So how do we find vector w1? So according to the Gram-Schmidt process, you're just going to take this given first vector in that basis. So according to this one, this is the first vector, and this is equal to vector 1, v1, and this is just 1, 1, 1. Okay, so this is w1. Next, we move on to w2. Well, for w2, the idea is we are going to consider the given vector, the second one, which is v2, and then we are going to subtract with the projection of this. This is the given one, so the projection of v2 onto what we have already obtained here. So this is the new result, so onto w1. So that's all that we can do because we only have w1 so far. Okay, and this is equal to v2. So if you want to project v2 onto w1, the formula is quite simple. So it will be w1 dot w1 multiplied with w1, and here will be v2. So next is we would like to find what is this. So we need to know what is that, and we can achieve that by finding the dot product of w1 with v2. And w1 is this 1, 1, 1. v2 is this negative 1, 1, 0. So you will get negative 1 plus 1, which is 0. Next, we would like to find this value. So that is w1 dot w1, and this is 1, 1, 1 dot 1, 1, 1. So it becomes 1 plus 1 plus 1, which is equal to 3. Substitute these values into this. Therefore, v2 is this guy, negative 1, 1, 0, minus, of course we know this is 0 over 3, which is going to be 0 later on, and this is w1, which is this one. So 0 multiplied with this, everything is going to be 0. Therefore, w2 is negative 1, 1, 0. So this is the result of w2. Okay, next is we are going to find what is w3. Okay, so we're going to stop at w3 because here we only have up to v3. Okay, so for w3, to find w3, we are going to use the vector that is given to us, which is v3, and we're going to minus the projection of v3 onto, well, we have got w1, so we're going to consider that on w1, and since we got w2 as well, so we're going to consider finding the projection of v3 onto w2, and that's it. Okay, so the formula is quite easy. Okay, I hope you are able to get the hang of it. If you want to find the projection of this onto W1, that means you have W1 here, W1 over here, W1 over there, and W1 right there, and up here is V3. So that is quite easy, yeah? And here is the projection of V3 onto W2. So therefore, we are going to have W2, 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 W2. And here it will be multiplied to vector V3. So this is V3. So that is the formula. Okay, now I need to find what is this value. Okay, so this value is not calculated yet, so we need to calculate. Maybe I'm just using this space. So W1 dot V3. So W1 is okay, W1 is, hang on, there's something wrong with my pen. Okay, so W1 is this, so 1, 1, 1, 1. Give me a second. So hang on, I don't know why is it not sensitive to my touch, this pen. Okay, let me try this one more time. So I'm just going to use this space here. W1 dot V3 is 1, 1, 1, and V3, so this is 1, 1, 1, V3 is negative 1, 0, 1. Negative 1, 0, 1. So here the result is negative 1 plus 1, which is equal to 0. Okay, so that is this part. And then for this part here, W1 dot W1, we have already calculated here. The answer is 3. And what I can do is I can write down what is V3. V3 is negative 1, 0, 1 minus 0 over 3, and W1 is 1, 1, 1. Okay, minus, now I need to find what is this value. So this is W2 with vector 3, and W2 is this one, negative 1, 1, 0, negative 1, 1, 0. V3 is negative 1, 0, 1. So this will be 1, 0, and 0. So this is 1. Right, so 1 over, now W2 dot W2. So this is negative 1, 1, 0 dot negative 1, 1, 0, and it becomes 1 plus 1. Okay, so 1 plus 1, this is equal to 2. Right here is 2. And what is W2? W2 is negative 1, 1, 0. And we're going to simplify and see what sort of result that you will get. Okay. Well, if you go on and try to simplify that, this will be negative 1, 0, 1. This will be 0. So minus negative 1 over 2, 1 over 2 and 0. And this can be simplified as negative 1 plus 1 over 2. So this is negative 1 plus 1 over 2. So this is negative 1 over 2. Okay. And here is negative 1 over 2. And this is 1. So this is W3. Okay. Therefore, I can write down the orthogonal basis is given by W1, W2, W3, and this is equal to, well, W1 is this one, 1, 1, 1, W2 is this one, negative 1, 1, 0, and W3 is this result that we have, negative 1 over 2, negative 1 over 2, and 1. So this is the orthogonal basis, and we are not done yet because we need the orthonormal basis. Right, so I will just erase this part. Well, to find the orthonormal basis, what you need to do is you need to calculate the magnitude of each vector here. Well, for this one, for example, the magnitude, which is given by this notation, is, well, 1 squared plus 1 squared plus 1 squared. So this is equal to square root of 3. Next, the magnitude of this is just negative 1 squared plus 1 squared plus 0. And this is square root of 2. And for this one here, magnitude of W3, negative 1 over 2 squared plus negative 1 over 2 squared plus 1 squared. So this is 1 over 4 plus 1 over 4 plus 1. So 4 over 4, 1 over 4, 1 over 4, that is square root of 6 over 4. And this can further simplify it as square root of 3 over 2. So this is the magnitude. Now the orthonormal basis. Okay, so to find the orthonormal basis, we are going to divide this with the magnitude. So 1 divided with the magnitude, it will be 1 over square root of 3. 1 divided with the magnitude, it will be 1 over square root of 3. Hang on. Okay. Okay. And here 1 divided with the magnitude, so 1 over square root of 3. So that is the first vector here in orthonormal basis. Next is negative 1 divided with the magnitude. So this will be negative 1 over square root 2. This one with the magnitude, so 1 over square root of 2. 0 with this is just going to be equal to 0. Okay, next is this one, negative 1 over 2 divided with square root of 3 over 2. So negative 1 over 2. When you divide with square root of 3 over 2, this is similar to multiply with square root 2 over 3. Okay. So negative 1 over 2 divided with this is equal to multiply with square root of 2 over 3. Similarly, here is going to be negative 1 over 2 multiplied with square root of 2 over 3. And this is 1 multiplied with square root of 2 over 3. Well, you can also simplify this part. For example, this part here can be simplified so that it looks a bit nicer. For example, okay, I'm just going to explain this part. How can you simplify that further? This is equal to, well, I can write down negative 1 over 2 is similar to negative 1 square root of 4, because negative 1 square root of 4 will give me negative 1 over 2, yes? And this is multiplied with 2 over 3 on this side. And we have square root and square root, so we can combine them together under one big square root. So this will be negative 1, 2 over 4 times with 3. So this becomes negative 1, 2 over 12, which is negative 1, 1 over 12, 1 over 6, sorry. You can cancel that out. 1 over 6. Now, of course, this can be further written as negative 1 dot square root of 1 square root of 6, which is just square root of 1 is just 1, so negative 1 square root of 6. So this here can be further simplified as this one. Okay, for this part here, the result is going to be similar. It can be simplified as negative 1 over square root of 6. Now for this one, okay, if you want to follow the same idea, so for example, here we divided with square root of 3, square root of 3, square root of 3. Here we got square root of 2, square root of 2. Here we have square root of 6, square root of 6. So if you want to write this in terms of square root of 6 as well, so we know that 1 times 2 over 3, we can try to express 1 in terms something over 2, so similar to this thing. So here is 2 over 2. 2 over 2 is multiplied with square root of 2 over 3. And again, following the similar idea, this is the same thing as 2 square root of 4, 2 over 3. And if you consider combining everything under one big square root here, it will be 2 over 4 times 3, and you will get the same result, which is for this one, it can be simplified to 2 square root of 6, 2 over square root of 6. Okay, so this is how this part here can be simplified as such. Okay, let's look at the last example here related to the Gram-Schmidt process. Here we have U as the subspace of vector space here, real numbers and 4 dimension, and we have this basis v1, v2, v3, and it is defined as such. So using the Gram-Schmidt process, you are asked to find the orthonormal basis, and our starting point is, of course, to find what is orthogonal basis. So find the orthogonal basis first. So in order to find that, again, since they use v1, v2, v3, I'm just going to define my orthogonal basis as w, where w1, w2, and w3. So I need to know what are the values of those. So according to the Gram-Schmidt process, w1 is going to be equal to v1, what's given here, and this is equal to 1, 1, 1, 1. Okay, so that is W1. Next, if I want to find what is W2, so W2 will be, we're going to get what we know about the second vector in this basis here. So this will be V2, and since we know W1, we can find the projection of V2 onto W1. So this is what we're going to do. And again, the formula is, well, I'm just going to repeat the formula. You want to find the projection of V2, therefore onto W1. Okay, so therefore we will have W1, 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 and V2 will appear here on the numerator part. Okay, just one time. Okay, well, I need to know what is W1 and V2, the dot product of W1 and V2. So I'm just going to use this space or whatever space is given here. So W1 and V2, W1 is 1, 1, 1, 1. V2 is this guy. So 1, 1, 2, 4. And I will get the same result here. So I will have 1 plus 1 plus 2 plus 4. This is equal to 6, 8. Okay, so W1 of V2 is 8. Well, let us just substitute what we have got so far. For V2, V2 is this guy. So 1, 1, 2, 4 minus. So this one here is 8. Next, I need to find the value of W1 dot W1. W1 is 1, 1, 1, 1. This is quite easy to calculate. So we have 1 plus 1 plus 1 plus 1, which is equal to 4. Write down the answer. And W1 is 1, 1, 1, 1. Okay. Well, we can simplify the process here. So we will have 1, 1, 2, 4 minus 8 over 4 is 2. So 2, 2, 2, 2. And this is equal to 1 minus 2 is negative 1, negative 1. 2 minus 2 is 0, 4 minus 2 is 2. So this is the value of W2. Okay, next is to find the value of W3. So to find W3, we're going to use what is given to us, this vector V3, V3, and we are going to find the projection of V3 onto what we have already got, onto W1. So onto W1. And we're going to find the projection of V3 onto what we have already got, W2. So up to that. Okay. And the formula here is going to look like this. Projection of V3 onto W1, that means we have W1, W1 dot W1, and here is also W1. V3 will appear once on the top. Similarly for this, projection of V3 onto W2, so here we are going to have W2, W2 dot W2, here is also W2, and this is V3. Okay, so our next job is to find what is W1 dot V3. Okay, well, okay, so W1 dot V3, well, W1 is 1, 1, 1, 1, and V3 is this guy, 1, 2, negative 4, negative 3. So if you consider the dot product, you will get 1 plus 2 minus 4 minus 3, negative 7, plus 3 is negative 4. Okay, so we just substitute whatever that we have so far. V3 is 1, 2, negative 4, negative 3. This is V3 minus, this is negative 4. Okay, now W1 is 1, 1, 1, 1. So what is W1 dot W1? This has already been calculated here, and the answer is 4, so we just substitute that straight away. So this is 4. Next, we continue with finding what is this value. Okay, so this is W2 dot V3, and W2 is this one, negative 1, negative 1, 0, 2. And V3 is this guy, 1, 2, negative 4, negative 3. So here it has negative 1, negative 2, 0, minus 6. So this is negative 9. So the value of it is negative 9. Just substitute it straight away. Next is to find what is W2 dot W2, which means this one here, negative 1, negative 1, 0, 2, dot with negative 1, negative 1, 0, 2, and the answer is 1 plus 1 plus 4, which is equal to 6. Okay, so this is 6. Now what is W2? W2 is this guy. So W2, so this is W2 is negative 1, negative 1, 0, and 2. Okay. Well, we can go on and try to simplify the result. Hang on, give me a second to just erase everything here. Okay, and this can be simplified as 1 to negative 4, negative 3. This is plus 4 over 4 is 1, so we will get back this notation, this 1, 1, 1, 1, 1. This is plus 9 over 6 is actually 3 over 2. Yep. And here we have negative 1, negative 1, 0, and 2. And I think we can just write down the answer straight away. Okay, so here will be 3 over 2. Yep, so just going to write the answer straight away. This will be negative 3 over 2. This will be negative 3 over 2. This will be 0, and this will be 3 over 2. So here will be 18 over, which is 3, yeah? 3 over 2, so 3. Okay, so this is the result. Well, then you can simplify that. 1 plus 1, negative 3 over 2. So 2 minus 3 over 2, this will be 1 over 2. 2 plus 1, 3, minus 3 over 2, you will get 3 over 2. Negative 4 plus 1, 0, negative 3, negative 3, 3, so this is 1. Okay, and this is W3. Well, based on this, I can write down the orthogonal basis. Therefore, orthogonal basis is given by this set of vectors W, and this is equal to W1, W2, W3, and I can write down the result. For W1, it is 1, 1, 1, 1, for W2 is this one, -1, -1, 0, 2. And finally for W3 is this one, 1/2, 3/2, -3, 1. So this is orthogonal basis. And the question is asking you to find the orthonormal basis. Therefore, we need to continue our work with finding the magnitude for each of these given vectors. Okay. Right. Magnitude for vector W1 is just 1 squared plus 1 squared plus 1 squared plus 1 squared. This is square root of 4, which is equal to 2. So that is the magnitude. Now, this part is done. The magnitude for W2 is -1 squared plus -1 squared plus 0 squared plus 2 squared, and this is 1, 1, 4, so square root of 6. Okay, next is this one. The magnitude for W3 is 1/2 squared plus 3/2 squared plus -3 squared plus 1 squared, and this can be simplified as 1/4 plus 9/4 plus 9 plus 1, so 10 plus 10/4, so that is 12/5. So we will have that as, well, 10/4 is 2.5, so 12.5, and that is just, well, we can write it in this form, 25/2. 25/2 is equal to square root of 25 square root of 2, which is just 5/square root of 2. So this is the simplified version of the magnitude of W3. Based on the magnitude here, we can then find the orthonormal basis. So therefore, the orthonormal basis is going to be, for the first one is, all this thing here will be divided with the magnitude. So we have 1 divided with the magnitude is 1/2. So everything is 1/2. That is the first one. Next is this one will be divided with the magnitude. So we have -1/6. This one is also -1/6. This one will become 0. This is 2/. Oh dear God. Okay, there's something wrong with my pen. Okay, give me a second. So PowerPoint is unstable. No. Oh no, come on. Okay, I think I'll just end the presentation here. I'm sure you can proceed on your own, and you should be able to find the orthonormal basis for this question here. Okay, right, thank you very much. I can't even end this presentation.